Okay, so solutions to the practice exam, number 2. So, um, for number 1, we're asked to compute 4 separate quantities: the unit tangent vector, unit normal vector, binormal vector, and the curvature. And helpfully, on the cover page, there are these 4 formulas, which are what we will use to answer this problem. You're actually given 3 ways of computing curvature, so it's possible that the problem can be slightly altered to make use of the other versions of the formulas. But the way that this problem is set up, this is the formula that makes the most sense to use. You could, in theory, use the other one. I think it's r dot r prime, or maybe it's the first derivative cross the second derivative divided by some magnitude. That one is possible to use, but uh, because along the way you're already computing t prime, it makes sense to use this formula. Okay, so let's take a look at this. I'm not able to scroll. That's weird. What about now? Okay, it's a little bit bothersome. Okay, right, so for the tangent vector, we're just going to use this formula, which means that, well, we have to take the derivative and then take the magnitude, so that should be pretty straightforward. Yeah, each of the terms is pretty straightforward to take the derivative of. Then to take the magnitude, we square each of the components, sum them together, and then take the square root of them. And then these 2 terms, you can see that um, you factor out a 16, and then you get sine squared plus cosine squared of the same argument, which means that that becomes 1, the sine squared plus cosine squared. You have a 16 then. And then that simplifies, right? This is 25, and so square root of 5, or square root of 25 is 5. Okay, then dividing these two, as per the formula for the tangent vector, gives you this vector function. Okay, next for the normal vector, principal unit normal vector, you have to, you're using this formula, so you need to compute t prime and its magnitude, and then divide. So t prime, well, we computed t, so we take the derivative. Yeah, that looks pretty straightforward. Just have to be careful with negatives and make sure that you pop the additional 4 out from chain rule. Taking its magnitude, again, you'll end up squaring this quantity and this quantity, this cosine squared here, and the, I should maybe use this. The cosine squared and the sine squared will combine together, giving you 1, and so the only thing that you end up getting is the coefficients in front, the negative 16 over 5. You end up squaring that and then taking the square root as per the formula for magnitude. And so this is the magnitude of t prime here, and then you would divide in order to compute the normal vector. So dividing is going to get rid of the coefficient in front, well, except for the negative. And so you end up with this as your unit normal vector. And then for binormal vector, you have this formula, tangent vector cross the normal vector. So then you would set up the determinant for, expression, because that's how you compute a cross product. You insert the vectors in order, so t is the second row, and n is the third row. And then you go ahead and compute the normal vector, or you compute the cross product. Now, I should perhaps talk about this in a bit of detail, because I think that there were some people that couldn't compute things correctly on the first exam. So when you compute the the function in front of the I term, it's this submatrix. So it ends up being this submatrix, and you end up doing this main diagonal minus the anti-diagonal. And so you end up with, yeah, this expression. And then that expression is going to simplify. because the sine squared plus cosine squared. So you see it becomes 4 over 5. With J, you end up having this submatrix. So another way of thinking about it is that you kind of cancel out these two, this row and column. So you're left with those four terms. And so then the main diagonal are these two elements, and the anti-diagonal would be these two elements. So you multiply them, and then you see that there's a negative in front because of sign alternation. And then for the K, for the last part of this determinant, you cancel out this row and column, you're left with this submatrix. And so you have this main diagonal, that anti-diagonal, multiplying. The 0 is helpful, right? You just have that. And then those two don't change. Okay. So, then the last part of this problem is to compute the curvature, and it's convenient to use this formula. So, looking above, we see that we computed the magnitude of t prime, 16 over 5, and we computed r prime early on. It's just 5, and so we can combine these together to get 16 over 25. Okay, that's number 1. For number 2, I want to use a different color actually. Number 2, this is a problem involving the multivariable chain rule. So you're given a function f of x and y of r and theta, x of r and theta, and you're asked to compute df dr and df d theta. So you could set up this diagram, you could scribble this off to the side somewhere, or you could kind of just do it mentally if you're comfortable enough with setting it up. I don't know. For me, I don't need to draw the diagram, but I did it here just in case you guys find it helpful. So computing df dr involves the paths going from f to r. So you have one path going through x and one path going through y, and those will set up these two terms in the multivariable chain rule. So df dx times dx dr and df dy times dy dr. And then you can compute that. Before doing that, let me also just say the ones for d theta. So going for doing df d theta is the paths going to theta, so df dx times dx d theta and df dy times dy d theta. And yeah, computing these partials. So df dx, you can look at this and see this just uses power rule, more or less. So 2x minus y would be df dx. df dy would be minus x plus 6y. Remember that with partial derivatives, you treat the other variables as being constants. So just pretend they're numbers and take the derivative like you are used to, all the derivative rules. What else do we need? We need the partials for the functions y and x. Okay, so we'll start with y. So the partial derivatives for y are dy dr, so that is going to be sine of theta, and dy d theta, which is going to be r cosine of theta. And then for the partial derivatives for x, it's dx dr and dx d theta. Dx dr would be just cosine theta. Dx d theta would be minus r sine theta. So those are all of the partial derivatives that can show up. And for me, I don't bother with like writing them off to the side because I can kind of compute them in my head pretty quickly. Maybe if the problem is sufficiently messy, it would be worthwhile to do that. But here it's pretty much just insert the things in computing it, the partial derivatives in your head. So one thing to note is that I didn't bother to bring all the variables down to the same level. So you see that I'm mixing the xy layer and the r theta layer. We have expressions that combine the two. You could, if you wanted to, then replace x and y with their definitions, right? r sine theta and r cosine theta in order to bring the expression down completely into this r and theta layer, so that these partial derivatives could be written completely in terms of r and theta. That might be better in some circumstances, but because the problem didn't specify anything of that nature, I didn't bother to do that. Yeah. Okay, number 3. So computing this limit of this vector valued function. Well, as you should recall, all you have to do is apply the limit operation to each of the component functions. So we pass the limit into each of the component functions, and we compute these limits. The only one that needs a little bit of work is the first one. So let's just quickly talk about the other two. So with this one, you can see that polynomial over polynomial, they have the same degree, so it's ratio to leading coefficients. So it's 2 divided by -1, which gives you -2. For the third guy, let me make it a little longer. What does that do? Very long. Okay, well, yeah, for that guy, the easiest way is to recognize the negative exponent as putting it into the denominator, and then you're taking the limit. So taking the limit, that ends up becoming 1 over infinity, which is equal to 0. So that's easy to see. For this one, you have to use L'Hopital, right? So when you take the limit, when you naively plug in, you get infinity over infinity. So you have to use L'Hopitals to resolve what the value actually is. And after just one application of L'Hopitals, you end up with 0 over infinity, which is 0. So not too bad. Okay. Let's see, for part B, so this is quite unrelated to the limit, that's fine. So this is just a computation, I think. You have to remember what is the formula for the tangent plane. Can also be phrased as the linear approximation at a point. So basically, it would be this formula. Yeah. So whatever the point is, you would end up plugging in at the point, and then this would be A and B would be if your point is equal to A comma B. That's how that works. So compute all of the necessary components and then plug in. So the necessary things are f evaluated at the point, f prime evaluated at the point, and f f sub x evaluated at the point, and f sub y evaluated at the point, the partials with respect to x and y. So the computations, you just have to make sure you don't mess up arithmetic. The arithmetic was easy in this case. I think probably the arithmetic might be slightly harder with the actual exam, so just make sure to, I don't know, double check your calculation, I guess. Right, plugging in. So, okay, let's talk about the partial derivative. So, partial derivative of f with respect to x, actually want even longer. So, partial derivative with respect to x, the y is a constant, so you just have this x squared becoming 2xy, that's this term. And then the partial derivative of this square root function is going to be just 1 over the square root function. And then you would have a chain rule coming from the inner function of x plus y, but that's just 1 when you take the derivative with respect to x. So that's nice and simple because the inner function doesn't have anything complicated in it. If you had x squared, then the chain rule would actually give you something. Let's see, and then the derivative with respect to y is going to be x squared minus the same radical expression. So you get the same 1 over 2 root x plus y. Right, for the partials. Okay, plugging in, straightforward here, and then you plug into the formula for the tangent plane. So we're using z on this side because it's asking for the tangent plane. If it asks for the linear approximation, I would then express it as L of x plus y is equal to, and then it would be the same expression. on the right-hand side, right? So this is the point that you're centering your plane at. You're forcing your plane to pass through this point. Well, it's this piece of data along with these two is what forces it to pass through the point that is specified, in this case 1, 2. And then these two factors are to make the slopes match up in the corresponding x and y directions, thereby making that plane a tangent plane. Okay, and then yeah, you can see that we feed those values that we computed beforehand into the expression. Right. Let's see. Number 4. Find all of the first partial derivatives and second partial derivatives of this formula, or well, this function. Okay, so right here the x derivative is a little bit more bothersome due to the fact that there's a chain rule, or not a chain rule, a product rule here. So notice you have two functions of x, so there's a product rule there. Y squared is thought of as a constant, so we pull that out and then we just take the derivative of x times ln x, and that gives you this. And then derivative of that with respect to x is straightforward. Now the derivative with respect to y, we have kind of the reverse situation. These two functions of x are treated as constant with respect to the y derivative. And so the only thing we take the derivative of is the y squared, giving us a 2y. And then I insert the x and ln x. Okay, and then this term goes to 0 because this whole thing is a constant with respect to differentiation by y. Okay. Then for the second partial derivatives, so I write all of them. So starting with the function f sub x, we take the x derivative and the y derivative. So the x derivative, well, this part is a constant, the y squared. This one, we take the derivative to x, that gives us 1 over x, which combines to give me that term. And then taking the derivative of that gives me that. Taking the y derivative now, well, this term goes to 0. And this is treated as a constant with respect to differentiation by y. So we only take the derivative of the y squared, giving us a 2y, and then times that factor. Okay. Now notice that these two are equal, but I didn't do that by just knowing, what is it called, Clairaut's theorem? I actually did take the y derivative of this, so, or the x derivative of this. So the x derivative here is not too bad. So you have a 2y that is treated as constant, and then you have the x ln x, which you need to take the derivative of. Maybe I'll write it like that. So that's product rule, and you get ln of x times, or ln of x plus x over x, which is 1, right? Ln of x plus 1. And then for the derivative with respect to y of this, the 2x ln x is a constant with respect to differentiation by y. So we are only taking the derivative of the function y, which is just going to be 1, which gives us that. Okay. Let's see, 5. So, oh yeah, this one asks you to compute two limits that are multivariable limits. Right, so the first one is straightforward. You can just plug in and then you see that there aren't any problems that arise. You actually get a number out of it. So that's always the first test that you should do with limits, is you just try plugging things in. Technically, there's something to do with continuity there, but pretty much all the time. If you plug in and it works, that means that that is the limit. I'm struggling to think of an example where that's not the case. So, yeah. Anyway, now with this one, if you try to plug in this one, you get 0 over 0. So that doesn't work. So, well, the only recourse that we have is to try approaching the point from different paths, approaching this point 0, 0 in different paths, and somehow getting two different values, making it so that the limit doesn't exist. We don't really have a way of showing the limit does exist in this kind of weirder situation. You can maybe reason about it through some other means, but usually such problems will indicate that the limit shouldn't exist if we have it that we can't just plug in right away. So let's go ahead and think through this. So when we approach along the x-axis, so pictorially that's like you're going this way. I mean, technically you can go from either side. So what you do is you set y equal to 0 into this function, and so that makes the numerator 0. That makes this term go to 0, and you're just left with this term, x to the 6. So the limit, this two-dimensional limit, becomes this one-dimensional limit, and then this function, well, clearly is just 0, so the limit ends up being 0. And then you have to kind of I don't know if it's messing around with it necessarily, or if you can kind of see right away, but you have to choose a function y, or you mess around and you try different functions of y where you think that it doesn't work. And usually what's going to have to happen is you need something to cancel between the top and bottom. So, for instance, like if you used y is equal to a line passing through the origin, you'd end up with x to the 4th over x to the 6th plus x squared. So you get some cancellation, and I think this was actually the first thing that I tried when I saw this problem. But you end up with this kind of situation, and then this still gives you a limit of 0 over 0 plus 1, which is equal to 0. So that doesn't work. But what does work is if you make it so that these two end up combining together and equaling the same quantity, which only happens if you have that y squared is equal to x to the 6th, which means that y is equal to x cubed. That's kind of the way that I figured out what would be a useful curve for y, a useful thing to set y to be equal to so that this resolves. So that's how I arrived at this. It was kind of by playing around. It's not necessarily obvious. Maybe with practice it becomes obvious, but yeah. So somehow or another you mess around and you get to this. And then by plugging this in for y everywhere, you end up with this limit. Now this is a one-dimensional limit. And then simplifying is going to give you that term. And then you see that the x to the 6th and x to the 6th cancel, giving you just 1/2. So the limit is 1/2. And now the point is that these two values, they are not equal. Not equal. Which means that the limit doesn't exist. Let me see. So explaining why not, perhaps another sentence is needed to say why we can conclude. So maybe I should have additionally wrote that we found two paths that gave two different results. So it's like approaching along this path wants the limit to equal 0. Approaching along this path wants the limit to equal 1/2. They're not the same, so the limit doesn't exist. Something along those lines. You can phrase it however you want. Okay, let's see. So I think there's a second last question. So for number 6, we have this function, f of x, y, and z, and we're asked to find the gradient. So the gradient is just the collection of partial derivatives. So you are computing, let's see, df is equal to f sub x, f sub y, and f sub z. So the partial with respect to x, with respect to y, and with respect to z, since f depends on x, y, and z, or depends on, yeah, it's a function of those variables. So that's how the gradient is defined. So we go ahead and we compute those partial derivatives. So derivative with respect to x, these comes 2xy plus z squared. This term goes to 0 since it doesn't have an x in there. Next, for the partial derivative with respect to y, you end up with x squared plus 2yz, right? And then for the partial derivative with respect to z, you end up with y squared plus 2zx, which is that one. Okay. Next, the directional derivative in the direction of this vector. So the first thing to note is that with directional derivatives, your direction needs to be a unit vector. And this guy is not a unit vector. So when you compute the magnitude of this, you end up squaring each of these components and then summing them together. So you end up with that quantity, which is root 6. And so in order to compute the u that you're going to use for the directional derivative, you should normalize, divide by the magnitude of v. So you end up with root 2 divided by root 6, and then doing that computation, root 2 over root 6, which simplifies to root 1 over 3. And then you can simplify that further, or the way that it looks. You can write it in a number of different ways. I wrote it this way because it just looks nicer that way. Okay, and so that's my normalized version of v. And so the directional derivative, well, it's defined to be the gradient of f at the point dot producted with the direction that you're taking the derivative with respect to. So you can rely on the previous computation for the gradient, right? I'm just taking part A and I'm plugging in this point into the form that we computed. And this is a rather simple computation because, yeah, everything is 1. So, like, x, y, and z are all 1. So this is just 2 plus 1. This is 1 plus 2. This is 1 plus 2. So you get 3, 3, 3. And you're dot producting this with the unit vector that we computed. And so we end up with 3 over root 3 times 3. And, well, one of these will cancel, which gives you 3 root 3. Okay. Right, so this should be the last problem. So we have this vector function, and we're asked to find the arc length function. So this is something that you have to remember. The formula for the arc length function is this. So you're integrating over the so I wrote this as ds. That's how I thought of it, as it's the differential element of arc length, which ends up being r prime, the magnitude of r prime. And so all you have to do is compute this expression. So derivative of r in this case is pretty straightforward. And then r prime magnitude, you square the two, square these two functions. That sine squared plus cosine squared is going to combine together, becoming 1, so you end up with 6 squared, giving 36. All of that is equal to 40, and then I can pull a 4 out of this. So we get root 4 times root 10, and so this becomes 2 root 10. So one thing I guess I should comment about this, right? The fact that in this expression we're taking this magnitude, which means that we have to ultimately this ends up being a square root of, I guess, x prime, y prime, and z prime. If you write it out in full, it'll be something that looks like this, where x, y, and z are the component functions. So the fact that there's a square root there means that this integral has to be pretty nice. The function has to be chosen pretty nice for the integral to even be computable, which usually the standard types of problems are going to be helixes, and this is a helix, right? The fact that we have these two, the cosine and sine, means that there's a circle in the xy in the yz direction, so it's spiraling in the yz direction, and it extends in the x direction. So if this is x, it's a helix that's like that. Yeah. Okay. All right. So let me say. Okay. Right. Magnitude here. That's just this number. We integrate that. Integral of a number is pretty easy. You end up just getting the t there. So that is our arc length function, s of t. And this is the part that is probably confusing. It's hard to explain how, like, the way that this works, I find. So so this formula gives us a relationship between the variables s and t, between the arc length and the time parameter. So what we can do is reverse this. That way we're used to thinking of this as given some time, t, compute the length. Give me back the arc length. Well, we want to kind of reverse that relationship. Given an arc length, we want to compute the time. And so to do that, we create the inverse function, which for this just amounts to dividing by that quantity. And now that we have this expression, we can think of this as a relationship that given some arc length, we get back some time. The reason that we do that is because we were given this parametrization of a curve in terms of t, and I want to produce a parametrization of the curve in terms of arc length. So really what I want is some way to, I want to like be able to feed in an arc length. How should I say? Given an arc length, I want to convert it to a time and then plug it in to my vector function r of t. And that's what this is, the t of s function that we've just produced. So we compose. That's what we're doing. We compose. Let me zoom out a little bit. I should be able to, I think. Please. Oh dear. Okay, there we go. So yeah. All right. So yes, we have that function, and then what we're doing is we define r of s by composing it with this t of s function. So given s, we then convert it to t using this relationship that we created, and then we plug that straight into the r of t that we have, which just amounts to substituting everywhere that we see t in this definition, we replace it with the expression. So the expression s over 2 root 10. As you can see, that is what ends up happening. The 2's cancel, and we just end up with root 10 in the denominator for everything, because helpfully there's 2's everywhere in each of the component functions, so the 2 gets canceled, and we're just left with that. Yeah, and I guess I don't have anything else to say, so that's that.